Okay, so let's continue where we left off. We had this limit as n goes to infinity of the absolute value of -1, and then you had the absolute value of 0.452 to the n plus 1 over 0.452 to the n minus 1. Then we had the 2 to the n minus 1 factorial over 2n plus 1 factorial. So let's take a look here and see how we go. We had the 0.45. You can subtract the exponents because 2n plus 1 and 2n minus 1, we have the same base of 0.45, so you can just subtract exponents and get your answer there. And moving forward from that spot, where do we go? Well, you can look at the 2n plus 1 factorial down below as what's the previous term? Well, it would be 2n plus 1 minus 1, which is just 2n. And the term before that would be 2n minus 1. And notice we could keep on continuing on down, but rather than continue all the way on down, we'll just write a factorial. And why might we stop that factorial right there? Well, the reason why, if you take a look up above, we have 2n minus 1 factorials in both spots. And so those 2n minus 1 factorials will immediately cancel. Okay? So we get something that goes like this. Okay? So we have 2n minus 1 factorials have gone away now. And what are we left with? Well, notice when we subtract this, you get the 2n's will cancel. You get minus 1. Oh, I'm sorry. This was a 2n plus 1 minus 2n minus 1. So that makes 0.45 squared. We get limit as n goes to infinity of 0.45 the quantity squared all over 2m plus 1 times 2m. Okay? So now, what happens? Well, there is no n involved with the constants up there. And all you're left with is the 2n plus 1 and 2n down below. And so what does this make? Well, this whole thing goes to 0. Now, that's fine because in the ratio test, we just need it to be less than 1. Remember, 1 is the inconclusive case. So since it goes to 0, we know that the summation n equals 1 to infinity of -1 to the n minus 1, 0.45 to the 2n minus 1, and then all over 2n minus 1 factorial is absolutely convergent by the ratio test. It's really a beautiful test when it comes down to it. So you get that one works out pretty nice for us in terms of what happened there. So questions on that ratio test and questions on the factorials, the same idea happens. So oh, okay, yeah, no big deal if you didn't answer something when I started the YouTube session back on. But at the end of the day, the big thing is notice what cancels. You're having the 0.45s, and this is going to happen in general actually. If you have some constant raised to some nth power, you're going to have so many terms of that constant cancel out, and you're going to be left with the constant raised to some finite power. The factorials will usually leave some remnants of the factorials in terms of there'll be a couple terms, there could be multiple terms, there might be one term, but it'll either appear in the denominator or in the numerator depending upon the scenario. So that's the main thing to take away on this, and the trend happens over and over again. Why were there two terms here? Well, I'll tell you exactly why. It was that 2n, that 2 in front of the n there. If that was a 3, you'll have 3 terms. If there was a 4, you'd have 4 terms when you're doing this ratio test. That's essentially what happens all the time. So same song and dance can be applied in terms of our approach to these problems. So hopefully that makes sense on that one. That's a big one to kind of take note of. So one last one to look at before we go into the next bit. We have another alternating series. We want to determine if it's absolutely convergent, conditionally convergent, or divergent. Now what happens is we often want to go back into that ratio test, root test. They work very nicely. This one will not work with the ratio test nor the root test. What happens, the best approach, you can start to see it right away. Notice that the degree of our polynomials are 2, but the coefficients aren't really nice, and so just leaving that off, I won't even do much more than this. If we let Bn equal 3n squared minus 7 over 5 plus n minus 2n squared. Okay, then the limit as n goes to infinity of this Bn, so 3n squared minus 7 over 5 plus n minus 2n squared equals, well, it's going to be 3 over negative 2, right? So what seems like a long and complicated problem, we know right out the gate that has to be 0 in order for us to use anything else, like the alternating series test or things like that. But so since it isn't, this is negative 1 to the n, we have 3n squared, 7 all over 5 plus n minus 2n squared. This is divergent by the test for divergence. It's not the alternating series test that does it, it's the test for divergence, because we don't have a limit going to 0. Right, alternating series test can only tell you if it's convergent, so keep that in mind as well. Alright. Taking a look at that, all those alternating series and absolutely convergent, conditionally convergent, and all that stuff, we can also start to look at what the error of the alternating series is. And so in this one, let's start to look at the first few terms. I want to kind of see what happens. So when we look at this, let's start plugging in 1. So we'll start with a sub 1, and so that would be, notice that's going to be negative 1 to the 0, so that's just a positive term. So it's going to be 3 over 1 squared, or 3 over 1. Then it becomes negative, so I'll put a minus instead of a plus. And here's a sub 2, so this will be 3 over 2 squared, which is 3 over 4. Then it becomes positive again, and then we'll have a3. This is 3 over 3 squared. Well, so this is 3 over 9. Then a over 4, or a sub 4. Half, well, that'll be 3 over 4 squared. It'll be minus, so this is 3 over 16. Then we add in 3 over 25. Then we subtract 3 over 36. Then we add 3 over 49. And we continue in this format. Alright, so we have a5, a6, a7, so on and so forth. Well, let's see what happens in terms of anything. Let's look at just the first few terms. So my question is how close is this to the actual sum value? Well, let's take a look. So let's say, let's give this a name. So let's call this capital S for sum, right? And this A1 plus A2 plus A3 this is S3. So I want to see what is the absolute value, so we'll call this the margin of error essentially, of S minus S3, right? And then we'll kind of come back to the less than 0.003 or 0003. So when we're looking at this, notice our next term is negative, so it's actually decreasing from the increase of 3/9. So you decrease 3/16, right? But then we're adding in something that's a little bit larger than a little bit smaller than 3/16 to make it not as much of a negative. And then the next number that we're subtracting is actually smaller than 3/25, which means it's a little bit less of a positive. So meaning we're still between 3/16 and between 3/16 and 3/9 in terms of our values of what's going on here. So every time though, our subtraction is getting further and further away from 3/16 essentially, and getting closer and closer to the last 3/9 value being added in. So we can definitively state that this thing will always be less than 3/9 for sure. Okay, and so basically you can use that last sum value and say, okay, we're going to be in good shape. So if we did s minus Sn, we could say that this is less than. Now notice I'm putting a strict inequality here. I can start to get in some different values as well. You can go one term more essentially to the a sub n plus 1 if you want, but what we'll do is we'll keep it at a sub n for right now. Okay, because you can't get back to that term. In fact, the worst case scenario, you move one more term over and you're just oscillating up and down. So hopefully that makes sense in terms of our bounds on this. So with that in mind, we want our thing to be within an error of 0.003 or less. So notice a sub n, we have this as 3 over n squared, right? And so this would be less than 0.0003. Okay. So if I divide both sides by 3, what do we get? Well, actually, let's write this a different way. So we have 3 over n squared is less than, this is going to be 3 over 10,000. So if that's the case, well then this becomes, we can divide both sides by 3, 1 over n squared is less than 1 over 10,000. You can kind of cross multiply since both of these are positive, and you'll get 10,000 is less than n squared. Since we're dealing with just a positive, we don't need a plus or minus here, so you take the square root of 10,000, right? And so we get n must be greater than, oh, in this case we said it could be equal, so in this case we'll make it equal. So notice this means a sub n would equal 100, but so in terms of the number of terms, what would that be? We'd have 1, 2, 3, so you start at 1, go up to 100, so we can go 1 less than that. So we'll say the 99th term will suffice. Okay. And in general, what can I say is the worst case scenario actually here, I can expand this to the a sub n plus 1, right? So if I keep on going, what we were kind of talking about there was the error in that that extra term. Notice it wasn't getting any further than what's going on there. So that's all that we're looking at in those cases. So any questions on that piece? Okay, so were there any other questions in terms of what we were looking at before. You mentioned the factorials and stuff like that. Did you want to see another factorial case or whatnot? Oh, okay, so great question. What would I use this for? So say I'm trying to think of a calculator, right? A calculator gives you some sort of decimal approximation, so rather than listing out all the terms, they might have to show you 9 decimal places. So I want to find the error within 0.000, and so basically 8 zeros and a 1, right? And if I can do that, I'm good in terms of the display on a calculator. So if I just find, okay, how many terms do I have to have in order for that to happen of this approximation, well, I just plug in that many terms and I have the calculation done in a few seconds. So there's many other routes, but a lot of stuff, what we're doing is we're doing approximations, trying to find it close enough to just get by, right? And so that's where this stuff would come into play. Hopefully, does that make sense on why we would use that and whatnot? And so I went with the a sub n I was kind of working with. You could do the a sub n plus 1 in general. And that's what I'd highly recommend, is using this one. I just did a sub n because that's one of the bounds. A sub n plus 1 will be a sharper bound. And what we're going to do later on too, we're going to use these to approximate functions. Functions like e to the x, we're going to try and write them as a polynomial, and you'll see that it coincides with the polynomial for quite some time. Yeah, so the homework is pretty close, and so okay, you're going to give it the good old college try. That's great. Glad to hear it. So if you're ready, if you got any other questions, just let me know. I'll be happy to answer them. I'll kind of be checking the discussion boards and things like that. So if there's no other questions for tonight, we'll call it a night, and I hope you have a good one. Thanks for coming.